I'm Ramon Miranda. Welcome to Chemistry in Action, a weekly program for teachers, students, and other viewers interested in the living world of chemistry. In the past 3 episodes, we gave you some insights into how chemistry is really part of our everyday lives. We've also begun to look into measurements. Today, we will be continuing that discussion on measurement. Join us for the next, I'm measuring again, 30 minutes in our episode, Measurement and Calculation. Temperature is an intensive property of matter. This means that temperature does not depend on the amount of substance. For instance, if I pour part of this sample of water into another container to come up with 2 smaller amounts of water, their temperatures would be the same. Temperature tells us how fast atoms and molecules move around. The higher the temperature, the faster the motion. The lower the temperature, the slower the motion. The thermometer is commonly used to measure temperature. In the laboratory, you may come across a mercury thermometer or an alcohol thermometer. Mercury and alcohol both expand with increasing temperatures, but alcohol expands more than mercury for each degree rise in temperature. Thus, it gives us more sensitive readings. Besides, it is less expensive, and if it breaks, the alcohol vapor is not toxic. But unlike this mercury thermometer, the alcohol thermometer is only good for measurement of lower temperatures. Thermometers are marked in degrees based on either one of 2 temperature scales. In the Celsius scale, the freezing point of water is 0 degrees. Its boiling point, 100 degrees. In the Fahrenheit scale, the freezing point of water is 32 degrees and its boiling point is 212 degrees. In many scientific calculations, the Kelvin or absolute scale is also used. In the Kelvin scale, 0 degree is the lowest possible temperature that can be reached. You will learn about the significance of absolute zero in a future episode. Earlier, we discussed how important it is to measure mass and volume. Mass and volume are both extensive properties of matter. That is, they depend on the amount of substance. This brings us to another property of matter that combines measurements of mass and volume. This is density. It tells us how much mass or matter there is for each unit of volume of the sample. Density can be expressed in grams per cubic centimeter or grams per milliliter. Unlike mass and volume, density is an intensive property. It does not change with the size of the sample. That is why density can be used to characterize a given substance. Let's look at samples of substances, each with their own density. Among them, air has the lowest density. Water is 1,000 times more dense than air. Rubber is a bit denser than water. And steel is more than 7 times as dense as water. For a pure substance, density does not change with the size of the sample. These 2 water samples have the same density, but density does change with temperature. That's because most substances expand slightly as their temperatures are raised. Density generally falls with rising temperatures. An exception is water between 0 degrees Celsius and 4 degrees Celsius. Densities for different materials are listed in handbooks and and have been measured at 20 degrees Celsius. There are several ways to determine density. The method we choose depends on what kind of sample we have and how accurate we want to be. In finding out the density, we usually first determine the mass of our sample using a balance. We then find the volume of our sample using a method suited to our sample. Our demonstrator, Dr. Marcelita Magno, will show us how to determine density. We can directly measure mass and volume for liquid samples like water. Before starting, make sure that all the equipment is clean and dry. Turn on the top loading balance. Put the tare to 0. This balance has a sensitivity of 1/100th of a gram. In your own school, you may use a triple beam balance or a platform balance if this is what you have. First, determine the mass of the dry 10 milliliter graduated cylinder on a top loading balance. Pour about 10 milliliters of distilled water and reweigh the cylinder, this time with water in it. Remember to record the exact volume of water in the cylinder to the level of accuracy permitted by the graduations on the cylinder. The mass of the water is a difference between the mass of the cylinder with the water in it and the mass of the cylinder alone. Take the temperature of the water in the cylinder. Calculate the density of the sample. Compare it with the handbook density of water at that temperature. We can also get the density of solids with irregular shapes or appearances, like these pieces of copper. We do this by first measuring the volume of water the copper sample displaces in order to determine the volume of the sample. Into another clean and dry 10 milliliter cylinder, pour about 5 milliliters of water. Record the exact volume to the nearest 1/100th of a milliliter. Weigh several pieces of copper metal to the nearest 1/100th of a gram. Put them slowly into the graduated cylinder. Be sure that there are no air bubbles trapped between the metal pieces. Read the new level of the water. Calculate the density of the copper metal. If the calculated value is very far from the handbook value, it suggests that your copper sample is not pure. You can use this procedure for any other kind of solid, provided the solid does not dissolve in water or absorb water. After we absorb what we just discussed, let's have a few absorbing messages. The Philippines is very rich in mineral deposits. These consist of naturally occurring elements or their compounds mixed with impurities such as dirt and rock. From our mines, we obtain gold, copper, chromium, iron, nickel, and aluminum, to name a few. Minerals and metals have different densities. Chemists and mining engineers use this information to separate metals from the mineral impurities by way of froth flotation. This process starts by grinding the ore. Then, the powder is mixed in a tank of water and carefully selected flotation reagents like collectors and promoters. Later, air at high pressure is induced through the mixture, creating froth. Collectors tend to make the minerals such as copper sulfides avoid the water. They become attracted to air and stick to the bubbles. The froth contains a lot of air, so it is less dense than water and floats on top. The froth containing the concentrate is then skimmed off. Meanwhile, the dirt and rock or tailings, which are denser than water, sink to the bottom of the tank. The measurements we report must not only tell us how much we have of whatever we're measuring, they must also tell us how accurate these measurements are. The mass of this mango, for instance, here we measured its mass on a platform double beam balance. We got a mass of 233.1 grams. The first three figures we are sure of. The last we are not. You could say that the last figure, which is 0.1 gram, is between 0 and 1 gram. If we measure this mango on the top loading balance, we get a mass of 233.03 grams. Here, we are sure of the first four figures, but not the last, which is 0.03 of a gram. If we compare these figures, we notice that while the first measurement has three certain figures and the last uncertain one, or a total of four significant figures, the second measurement has more significant figures because it has a total of 5 significant figures. This shows that the measurements from the top loading balance have more significant numbers than the data from the platform balance. The number of significant figures, or the accuracy of the measurement we report, depends on how sensitive our measuring instrument is, in this case, the balance. Chemists and other scientists often use very long numbers. This may be very big numbers. The number of molecules in 12 grams of carbon, for instance. This amounts to the huge number 6 septillion, 23 sextillion, which, written down, looks like this. Take the Andromeda Galaxy. It is 20 quintillion, 700 quadrillion meters away from the Earth, and that is written down like this. Some values measured can also be very small numbers, like the distance between particles in a salt crystal, or the diameter of a red blood cell. In working with such long numbers, it is easy to make a mistake and drop a zero or lose a decimal place. To make it easier to work with such very big or small numbers, scientists often use scientific notation. In scientific notation, the mass of the mango would be written like this and read as 2.33 times 10 to the power 2 grams. The scientific way of writing numbers makes it easier to count the number of significant figures in a measurement. Suppose the volume of the balloon is recorded as 8,000 cubic centimeters. With this number, we are not sure whether this number has 1 or 4 significant digits. By using exponents, we can make things clearer. If the volume was actually measured to the nearest cubic centimeter, then this measurement may be written down like this. This easily shows that the measurement has 4 significant figures. The number of significant digits in a measurement is important, especially in calculations. The computed results of experiments can only be as accurate as the actual measurements. We have a general rule for calculations involving multiplication and division. The product or quotient may contain only as many significant figures as the measurement with the least number of significant figures. Look at this calculation. The first number has only 3 significant figures. The second number being multiplied has 7. Following our rule, we may not use this answer which has 7 significant figures. The measurement with the least number of significant figures is 3, as in 1.13. So the product should be reported as 5.79 meters squared, which also has 3 significant figures. The general rule for adding and subtracting is that the sum or difference may contain only as many decimal places as our measurement having the least number of decimal places. Let us suppose that to calculate the result of an experiment, we have to add these numbers. The sum has 3 decimal places. This means that this sum has a certainty greater than that of the least certain measurement, which is 677.1 grams. The measurement with the least decimal places, in this case 677.1 grams, has only one decimal place. The sum we report should then have only one decimal place, 722.6 grams. In measuring, it is important to know how accurate and how precise we are. To be precise is not necessarily the same as being accurate. To make things clearer, let's watch a game of darts played by Romy, Lito, and June. Let's see how each of these three darters play. You can see that Romy always hits the bullseye. He is both accurate and precise. Lito always hits a step away from the bullseye. Lito is precise but not accurate. June is erratic. His shots are sometimes near the bullseye and sometimes far from it. He never hits the bullseye. June is both inaccurate and imprecise. Most measurements are like the hits in dart games. They do not involve making a tally or a count of the number of objects where we can have perfect accuracy. In making measurements during experiments, we often work under conditions that make measurements uncertain, like the effect of a draft on air on the balance. For this reason, we might get slightly different figures for each measurement. Take the mass of this mango. We had two groups of students measure the mass of a mango. One group used the top loading balance. The other used a double beam balance. They made 4 measurements each and came up with this data. Which of these measurements should we report? In scientific measurement, the value we report is often the average of the values measured. In this example, the average values are 237.01 using the top loading balance and 237.6 using the double beam balance. The question now is, how precise are these measurements? To find out the precision, we calculate the average deviation. We compute the difference between each measurement and the average. We then get the average of these differences or deviations. We can then report the results as 237.01 plus or minus 0.01, the precise measurement for the mango using the top loading balance. From the measurement with the double beam balance, we can report 237.6 plus or minus 0.1 as a precise measurement. With more accurate measurements, we can come up not only with better technology, we can also develop better ideas of chemistry that help us more fully understand the world we live in and predict the changes taking place in the world around us. As we explored the world of measured numbers, our own measured time, 30 minutes, has run out. This past half hour, we've seen how density and temperature are measured. We also had a brief lesson in significant figures. I hope that you have learned significantly more about measurement and chemistry. Be with us next week as we once more tickle your chemical mind. This is Ramon Miranda saying good day.